Okay, I am Doug Miles with the PGI Compilers and Tools Group at NVIDIA. We develop Fortran C and C++ compilers for the high-performance computing market. Today, those compilers are available on x86 CPUs and NVIDIA GPUs. A little over a year ago, we started retargeting them to OpenPOWER CPUs, and I'm going to give you an update on our progress there. We will have a beta release in May. And I'm going to review what we hope to bring to the software development ecosystem and give some early performance results. So high-performance computing is expanding, as you've seen this week. Deep learning is really driving that expansion. The part of the market that we cater to is the classic high-performance computing market, engineering and science sites that do weather forecasting, climate modeling, structural analysis, and automotive crash testing, higher energy physics, classic HPC science and engineering applications. And the key factor about these applications is a lot of them are proprietary or research community applications that are continually evolving. They're used in source form at these sites, which modify them in various ways based on the science they're doing. And so they need to be compiled over and over and over again. They're primarily written in Fortran C and C++. And they need to be parallelized to run across hundreds or thousands or more processors using OpenMP or MPI. And more they're being accelerated on GPUs using CUDA or OpenACC. So this is the market space that we are aiming at. Who are these customers? In PGI's case, it's nearly every U.S. Department of Energy laboratory, DoD computing center, NASA sites, NSF computing centers, pharmaceutical companies, oil companies, and most of the international equivalents. And so they are the leaders in HPC, and a lot of them drive HPC forward. You heard Fernanda talk earlier about the work that Oak Ridge is doing. And in fact, Oak Ridge and the Lawrence Livermore National Laboratory are the lead customers for PGI's OpenPOWER compilers. They have them today and are giving us feedback and are really driving us forward to support that processor in a comprehensive way. And why do these customers use HPC compilers or need HPC compilers? The answer is performance. This is a look at the spec OMP benchmarks, which is a set of 14 science and engineering applications. In this case, we have production compilers on x86. So these benchmarks, the average performance running across all 32 cores of a dual-socket Haswell system. And the performance is normalized to GCC, which is the infrastructure compilers. GCC, G-Fortran, G++, the infrastructure compilers for Linux. They're on every system. So why do people use compilers from PGI or IBM or Intel or Cray? The reason is there is in a lot of applications a performance premium. And you'll see here that the Intel compilers, which are obviously very highly tuned for Haswell, deliver an average about 50% higher performance than GCC across those 14 benchmarks. And the PGI compilers are a little bit behind Intel, but competitive. And this is an absolute requirement for an HPC compiler. If you've spent millions or tens of millions of dollars on an HPC system and your application is of this profile, well, you're leaving a lot of performance on the floor. G-Fortran might be the most expensive piece of software that you never bought. But as we've seen, while this is a requirement, it's no longer enough. More and more systems are GPU accelerated. Jensen mentioned in his keynote yesterday that now 97% of HPC systems include some GPUs in them. And in the last top 500 list, over 20% of the systems on that list derived their compute power primarily from GPUs. And so GPUs are becoming more and more pervasive. And a little over 4 years ago, PGI, together with NVIDIA and a few other compiler vendors, and several representatives from the user community defined OpenACC, which is a directive-based model for parallelization of codes. And really, it's designed in a streamlined way so that you can parallelize code for offloading to a GPU, but those same directives can be used to parallelize the code for a CPU. And again, we have this capability available today. It is a user-driven standard. Every one of the applications you see there listed on the right-hand side of the screen, your left-hand side, has contributed to improvements in performance or features in the compiler. And several of them, the ports were started at the hackathons that Fernanda referenced in the talk that she kicked off early today. And the benefits of OpenACC are portability. So because these are directives, pragmas in C or C++, directive comments in Fortran, the code remains 100% portable to any compiler or system. So you have the portability benefits. And productivity-wise, relative to CUDA or OpenCL or a lower-level programming model, there's a huge benefit. Mark Govett at NOAA, in a talk he gave yesterday, talked about porting some Fortran code to a GPU last week, and he was able to move 800 lines of code from the CPU to a GPU in less than 10 minutes. And if you've ever written a CUDA program or an OpenCL program, you'll know that you just can't do that. And so the productivity benefits of it are huge. And our goal is that eventually it's no more difficult to parallelize code for a GPU than it is for a multi-core CPU. And we're getting ever closer to that goal as we progress here. And so all of this technology we are retargeting to OpenPOWER. And as I said earlier, we're within about 6 weeks of the first beta release. We've had several alpha releases to both Oak Ridge and Livermore. And all of the features that we support on Linux x86 today will be supported on Linux OpenPOWER. So Fortran C, C++, OpenMP programming, OpenACC programming, support for CUDA in Fortran. All of this is being integrated with a code generator, an LLVM code generator developed by IBM and the open source community. And we're on schedule to have the beta release in May and a production release in November. And the goal here is very simple. If you have an application that runs today on Linux x86 and is GPU enabled using OpenACC or CUDA Fortran, you'll be able to recompile and run it on a Linux OpenPOWER system. And there are a few caveats. If you're using SSE-specific intrinsic functions or certain ASM statements, well, there are barriers there. But most applications do not use those features. And in that case, you will be able to recompile and run from x86 to Power. And an obvious question is, does it work? How well does it work? And we're far enough along that we're building and running a lot of real applications. WRF, the Weather Research and Forecast Model, is an 800,000-line application. It's the most widely used weather code in the world. And you can take that code. You can put all 800,000 lines in one directory, have an x86 directory and a window open there, an OpenPOWER directory and a window open there, with links to that makefile. Type make in each of those directories and build the whole application. Same makefile, same compiler options, same source code, no changes, and produce executables for a Haswell on the x86 system and OpenPOWER on the Power system, and that version of the code will run over 2x faster than G-Fortran compiled code on the Haswell and almost 2x faster on the OpenPOWER. And we're already running millions and millions of lines of code every night in this mode. And this is what we bring to the ecosystem. We want you to be able to easily move your x86 code to OpenPOWER with all of the GPU enablement that you have. And when you move to OpenPOWER with NVLink, you've heard a lot about that this week. From a compiler standpoint, that is a game changer. That allows us to think of data movement between CPU memory and GPU memory as an optimization. So the programmer can just focus on parallelization, let the system move data between host memory and device memory. And yes, you probably will need to, in some cases, go in and insert directives to optimize that data movement. But again, it gets us one step closer to the day when you can compile any code for execution on the CPU or the GPU and just execute it on the processor that's most appropriate for that part of your problem. And you heard earlier, Google is moving all of their infrastructure to target OpenPOWER to enable their applications to run on either x86 or OpenPOWER. And our goal is for all of those customers that you saw listed earlier, if you're a one-off scientist or engineer working on a code and you want that same capability to be able to run on either x86 or OpenPOWER to move your code, these compilers will enable you to do that. If you're an OEM or system builder, we want to engage with you. We want to make it easy for those customers on your prospect list to be able to do that same thing. So with that, I will stop and happy to answer any questions if there are.